Hello and welcome to my tutorial on hydrogen bonding. So, what is a hydrogen bond? Molecules containing OH or NH are polar and they have permanent dipoles. The dipoles are very strong. The permanent dipole-dipole interaction between molecules containing OH and NH bond is given the name hydrogen bond. In a hydrogen bond, the electron deficient H delta plus on one molecule attracts a lone pair of electrons on an oxygen delta negative and a nitrogen delta negative on another molecule. So this can happen in either nitrogen or oxygen molecules and hydrogen. Hydrogen must be present. So a lone pair is slightly attracted to the positive hydrogen and these delta charges form. And this bond can form very strong van der Waals forces, and that's what keeps the surface tension on this pond skater's legs. It prevents it falling in the water basically, as the hydrogen bonds are formed, and it sort of forms a very thin layer on the water, so the pond skaters can skate along water. And what is the special properties of water? So ice is less dense than water. Solid water is less dense than liquid water. This is because the ice is an open lattice in which hydrogen bonds holding the water molecules apart. When ice melts, the hydrogen bonds break, allowing the water molecules to move closer together. Water has high melting and boiling points because it has strong van der Waals forces. These extra forces have to be overcome in order to melt or boil water having high melting and boiling points. The extra intermolecular bonding from hydrogen bonds also gives water its high viscosity and surface tension. Hydrogen bonding in biological molecules. So hydrogen can also use to shape these DNA molecules or proteins. In DNA, hydrogen bonds hold the four bases in the double helix structure. The four bases are guanine, cytosine, adenosine, and T. They all bond together using hydrogen bonds. Thymine, that's it. Guanine and the cytosine both use three hydrogen bonds. Adenine and thymine use two hydrogen bonds. So if you want to find out more, go over to my biology tutorials. But back to the ice. If we draw a lattice of our ice, and then my hydrogen bond goes to the other one, and there's another hydrogen atom, and that is bonded to another oxygen here, and when these break, just these water molecules on their own are left. So when it's liquid, it cannot be in a crystalline structure anymore. That's when the hydrogen bonds break. So now move on to the next part. What is a metallic bond? Now, metallic bonds are the other kinds of bonds that you have to get familiar with. So imagine a metal atom. It has lots and lots of metal ions in it, and it has a sea of delocalized electrons because all those electrons are being repelled by the positive ions. So the atoms in solid metal are held together by metallic bonding. Positive ions occupy fixed positions in the lattice. Delocalized electrons are shared between the metallic structure, giving a strong attraction between a positive ion and delocalized electrons in the lattice. So high melting and boiling points are due to the electrons being free to move throughout the structure, but the positive ions remain where they are. The attraction between the positive ions and the delocalized electrons is strong. High temperatures are needed to break the metallic bonds and dislodge the ions from their rigid positions within the lattice. And they are also good electrical conductors because the delocalized electrons can move freely around the lattice. The metal can conduct electricity as the electrons have drift velocity. The definitions are: metallic bonding is the electrostatic attraction between positive metal ions and delocalized electrons. Delocalized electrons are shared between more than two atoms, and a giant metallic lattice is a 3D structure of positive ions and delocalized electrons bonded together by strong metallic bonds. So we'll now move on to next part, the structure of ionic compounds. The ionic lattices are strong electrostatic attractions between positive and negative ions. This strong attraction leads to very high melting points, as a large amount of energy is needed. The stronger the electrostatic attraction, the more energy is required to break them. So, the more powerful my ions are, then the more energy is required to break them. When an ionic compound is dissolved or melted, it can conduct electricity. So when the ions are mobile, they can move to either the positive terminal or the negative. So negative goes to positive and positive goes to negative. But the ions must be mobile and not in their fixed lattice, like that, like just there. So another example around here on hydrogen bonds is the attractions here. So the more hydrogen bonds one has, the higher the melting boiling point, and it's the same with the ions. The more electrostatic attraction you have, the higher the boiling point you're going to get. Now finally we're going to move on to the structures of covalent compounds. So simple molecular structures are molecules that are held together by weak van der Waals forces, and the atoms within each molecule are bonded by covalent bonds, like here. This is weak van der Waals forces here, and these have low melting points as the intermolecular forces are weak, so less energy is needed, and they do not conduct electricity. They are soluble in non-polar substances like cyclohexane. Van der Waals forces between the simpler molecular structure and the non-polar solvent. The formation of these van der Waals forces weaken the lattice structure. High melting and boiling points for giant covalent structures, because more energy is needed to overcome the strong van der Waals force. Giant covalent structures do not conduct electricity because there are no free charged particles except in graphite. Giant covalent structures are insoluble in both polar and non-polar substances, as the covalent bonds in the lattice are too strong to be broken up by the solvents. So if we look here at diamond, it has a tetrahedral structure held together by strong covalent bonds throughout the lattice. So it can't conduct electricity because there are no delocalized electrons, as all the outer cell electrons are used with the covalent bonds to keep it in that tetrahedral lattice. But it's very hard, as the external forces can be spread throughout the lattice. So if I really wanted to smash a diamond, I get another diamond and smash it, because that's the only thing that can break a diamond is another diamond, ironically. But anything else, it can absorb all the impact through the lattice. For graphite, though, it has a strong hexagonal layer structure, but with weak van der Waals forces between the layers, and it has good electrical conductivity because it has delocalized electrons between the layers, and as they're not all used up in making a fancy pants chemical structure. They're free to move parallel to the layers when a voltage is applied, so it can only move this way. It can't move up or down, only that way. And it's soft because the bonding with each layer is strong, and the weak forces between layers allow the layers to slide easily. That's why if I get a pencil, I can wear it out very quickly. But if I get harder pencils that of different mixtures of graphite, then it's harder for me to wear the pencil down. But if I got a really soft 2B pencil, then it is very, 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 very soft, because the bonding between A layers is very, very weak. So that's it for this tutorial. I hope you found this useful. I will upload exam questions on this. They tend to have written questions when it comes to covalent compounds and hydrogen bonding and metallic bonding. So I'll upload a few examples in later tutorials so you can have a go at them. But now we're moving on to the periodic table and how to use it effectively, and also we're learning about the group 2 elements and the group 2 compounds, and we're also learning about group 7 elements as well. So thank you for watching, and goodbye.